Welcome everyone to my course Formal Methods for System Verification. In today's class, we will learn normal forms for proposition logic. So, if you recollect, in the last class, we discussed the decision problem of proposition logic. So, what was exactly that? So, you have given a proposition formula. Your task is to check whether the formula is satisfiable or not. Right? So, we basically develop certain rules, inference rules, and we have shown that you can actually apply these rules and then you can actually reach to a decision, and we have shown that that particular process is sound and complete, right. Now the question is, when you have the formula, if it is in very arbitrary form, it will be difficult to develop your algorithm, right. Think about when you write a C program. If you don't know what is your exact input or the format of the input, you will not be confused how to write your algorithm, right. The same thing goes here also. So finally, for this checking the decision procedure, you have to develop an algorithm or a software, right, where you give the formula and it will check whether it's a set or not, right. So you should have some uniform way of representing your formula, Boolean formula or proposition formula, and that's called normal form, right. So normal form is what is it's basically represent the formula with some rules, syntactic properties in a uniform way, right, so that it have a what is your structure of your input. So in this class, we will primarily learn three normal form, what is called negative normal form, which is NNF, and then conjunctive normal form, which is called CNF, and disjunctive normal form, which is called DNF. This CNF and DNF is basically a subset of NNF. Okay. So in general, we will start with NNF, and then we will see what is the subclass CNF and DNF. And then we will also discuss how do you convert your formula into CNF or DNF, an arbitrary formula, and also we will discuss if your formula is in CNF or DNF, how do you check the satisfiability. Is satisfiability checking problem is it in that form or not? Okay. So that are the things we will learn in today's class. So let us start with negative normal form. So in this format, we allowed the negation with only the atoms, okay. So we will not have negation of the sub formulas, right, and we also only allow and or and negation. These are the three operators. So there are two things here. First thing is that the negation is not allowed over sub formula, it is only allowed over atoms. Atoms is nothing but the propositional constant, and you are allowing only three operator, negation, and or. This three operator is sufficient because you can represent any formula using this three operator, right. So to understand what we are saying, that this is not NNF. Why? Because this negation is given over sub formula, but this formula is in NNF. Why? Because the negation is associated with the atom A or the propositional constant A, and then this negation is also associated with the propositional constant B, and they are connected with OR. So this is NNF, but this is not NNF, right. So to give more example, it may be say not A or B and not A and C, something, anything is possible in this, right. I am not making any other restrictions, right. Say and not C and not D, anything is possible, right. So these are all NNF because my negations are always associated with the propositional constant, and I have only and or operator. We are not adding any further clause on this where the operator will occurs and all, right. So this is a more generic form of normal form. Now question is how do you convert your any formula into NNF? It is quite simple. You basically, if your formula does not have and an or negation, you convert them. Suppose it has implication, by implication, XOR and all, you convert them with the equivalent expression, right, and then you apply simply De Morgan's law, right. So what is De Morgan's law? It's basically, if you are taking a negation of this, how this formula will distribute, right. So this will be converted into this. It's basically not A, this will convert it into OR, this is and not B, and similarly if the OR is inside, the negation will make it and this negation will come with every atom, right. So this is very well known, De Morgan's law. And if we see if any other operator, let us say implication, I can represent in the equivalent form with only and or and negation. So, this is also well known. A implication B means not A or B. If you have XOR, A XOR B, which is nothing but A or not B, A and not B, or not A and B, right. Similarly, if you have by implication, it is A and B or not A and not B. Okay. So, this how I can convert the any other operator first into and or, and then I apply this operator De Morgan's law, so that I can bring this negation close to the propositional constant, right. This is what the basic standard process. To give an example, let us say I have a formula is this. So, what I will do first, I will replace this implication with equivalent one. So, not A or B, but B is here not B, right. So, this become this, and then I apply this De Morgan's law to bring this negation close to this. So, it will not A, so which is A, and or will become and then not B become B. So, effectively this is converted into this is NNF, but this is not NNF, right. So, this conversion is quite simple. Given a formula, I can easily convert into NNF. Okay. Now, I will move on to the next one, which is called disjunctive normal form or DNF, which is more common. The CNF and DNF is the most common one, which is a subset of NNF. Okay. So, here we, in addition to the rule that you have NNF, that means you do not have any other operator other than and or and not, and your negation is always associated with the atoms or the proposition constant. I also add an additional rule how your and or operator occur in your formula. Okay. So, it basically says that it is a disjunction of conjunction of literal, right. So, what is happening here is a conjunction of literal. So, you can think about conjunction of literal, say A and not B and C, this is conjunction of literal, right. So, you will have this there, and such conjunction of literal things will have a disjunction to connect, right. So, this is say 1, then you have or, you can have say A and B, or say C and not D. So, this is in DNF. Okay. So, you can clearly see that I am just adding additional constraint how your formula, this operator will occur, right. So, I am saying that and can occur only within, this is called clause, right, CLAU clause, and these clauses are connected by disjunction, right, and this negation can only occur with propositional constant, right. So, this is how your formula will look like, look it carefully. So, this is conjunction of literals, this is conjunction of literal, and those are called clause, and this clause are connected by disjunction. Okay. So, this is clause 1, this is clause 2, this is clause 3, right, and they are connected by the disjunction operator. So, understood. So, we have also one example here. So, this is conjunction of literals, conjunction of literal, conjunction of literal, and they are connected by disjunction, right. So, or between the groups. Understood. So, now the question comes, how do you convert your formula into DNF? Since the formula has to be in NNF first, what I will do? I will convert my formula into NNF first, so that I remove all other operator like implication by implication, and negation comes close to the this atom, right, and then I will apply the distributive property, right. So, the distributive property is this. Okay. So, here you see I have, this is clause 1, this is clause 2. So, clause should have or, and they are connected by and, but I need in other way, right. So, in the DNF formula you have and here, right, A or and B and C, or C and D, right. It's basically it has opposite of that, right. So, if you recollect here, I will have and in the clauses and they are connected by or, but here you see you have and connected the clauses and or inside, right. So, we have to distribute this and over or, right, which is quite common. So, what will happen, A and B or A and C. So, this is the distributed formula. Okay. So, now if you take this example, just to this, instead of A you can have multiple clauses, right, multiple literals. So, if you have this, again this is not in DNF, because you should have and here and or here in the DNF, but it is in other way. So, I will apply the distributed property. What I will do, I will distribute first x1 with this and then I will distribute y with over this, right. So, what will happen, equivalent formula, it is x1 and x2. So, x1 distributed with x2 and then x1 distributed over y2. So, x1 and y2 and then y1 distributed over x2 and y2, right. So, then y1 x2 and y1 y2. Okay. So, this is how I can just keep applying the distributed property to get my DNF formula. This is in DNF because you have conjunction of literals is the clause and they are connected by disjunction. Okay. Now, if I take a bigger formula, let us say I have 3 clauses, right, every clause let us say I have 2 terms. Okay. So, again what will happen, I will first distribute this x1 over all of them, then y1 over all of them and so on, right. So, what will happen, so x1 I will take x1, x2 and x3, right, x1, x2, x3, then x1, x2, y3, x1, x2, y3. So, initially happen x1, x2 and x3, then x1, x2, y3, x2 is done. So, then for x1 I will take y2, again I will repeat this one, right. So, x1, y2, x3, then x1, y2, y3, right. So, then x1 is done, the same thing I will now repeat for y1. So, y1, x2, x3, y1, x2, x3, y1, x2, y3, right. Then I will take y1 and y2, then y1, y2, x3 and y1, y2, y3. So, this is in DNF because you have disjunction in between and the terms has conjunction, right. So, how many clause I got here? 6, right, 1, 2, 3, 4, 5, 6, 7, sorry 8, right. So, can you relate this number of clause? So, you have clause 1 here, right. So, you have basically in this formula you have 3 clauses. So, in this formula this is clause 1, this is clause 2, this is clause 3. So, I got 8, so which is 2 to the power 3, there are 3 clauses, right, and each clause has 2 terms. So, now if you have 4 clauses, it would have been 2 to the power 4, 16 clause in the converted DNF, right. So, this way if you have a generic formula where you have n clauses, each have 2 term or literals, I will end up getting 2 to the power n clauses in the DNF formula. Okay. So, this is what problem, right. So, your original formula has n literals, right. So, for example, in this formula how many literals are there? 2n literals, because x1, x2 to xn and y1, y2 to yn. So, there are 2n literals and how many connections are there? For every literal n plus n minus 1. So, 2n minus 1, right. So, it is the size of the formula you can think about order of 4n minus 1, right. This is total size of the formula because you have 2n literals and 2n minus 1 Boolean connected, right. So, this is the overall size of the formula, but the generated formula will have exponential number of clauses. So, that is the problem, right, because even if you now have a decision procedure which is say linear time, which is polynomial time, let us say, but if your input is already in exponential, then what will happen? Even it will take exponential time, right, because your size of the input is exponential, right. So, this way of conversion DNF is problematic in the sense at the end of the day you get a DNF formula, but if you start with the formula is already in exponential size. So, no matter what is your algorithm, you need exponential time to process that formula. Okay. So, this is one of the drawback of converting into DNF. Now, let us see the complexity of satisfiability problem of a DNF formula. So, what is this? You try to understand that your formula is in DNF format now, right, which is conjunction of literal, which is and disjunction of the clauses in that formula. So you want to check the satisfiability. So what is satisfiability? You remember, right? I discussed in the last class that given a formula, you try to identify an input for which the formula is true or satisfiable, right? But if your formula is in DNF, it is easy to do, right? So let us see. Suppose you have the formula which is say A and B or C and D, right? So this is the formula. This formula is clearly satisfiable. So to check whether the formula is satisfiable, because you have OR in between, right? You have OR in between. You have say not A or B and so on, or say not C and D, right? So this is AND. So this is say not A and B. Okay, if you have this formula, so now let us say you want to check whether the formula is satisfiable or not. Because you have disjunction, right? You don't need to check all the term, all the clauses. Just checking one clause is enough. Because if you have OR in between, if you have one of the term, one of the clause become true, the formula will be true, right? I don't need to check the rest of the thing. So now you have one clause to check. Let us say I start with this clause. Now I have to just check, is there any value for which this particular clause is true or not. So now if the clause have say A and not A and B, this will be always false, right? Because if you have A and not A, if you take a AND, it will be always false. But if this particular clause does not have such thing, A and not A kind of thing, if you have something say A and B or A and C and not D, then it will be always satisfiable, right? I just assign say 1, 1 and 0, right? So this will be true, right? So D equal to true. So if the clause does not have A and not A for a literal, right, or a atom, that particular term is always satisfiable, right? And let us say this has A and not A, then I will check the next one. This also has A and not A, then I will check the next one. If that also has A and not A, then I will check the last one. So you are just checking the entire formula at most once, right? If you get the first term, in my case that is the case, I don't need to check the next one, right? Because I just say A and B, so I will just assign 1, 1. So this will become 1, I don't need to check the rest of the formula. But if you have this A and not A, let us say I have formula A and not A and B, or say C and D. So in this case, because it has A and not A, this clause is always false, right? Then I have to go to this one and check, oh, there is no C and not C or D and not D. So I will just assign 1, 1. So this particular will be true. So checking this satisfiability is easy in the DNF formula, right? Because you have to just scan the entire formula at most once. Most of the time it is not. You start with the clause 1, just check it has for any atom A and not A, both A and not A is present there, right? Both the atom and their negation is present there. If it is not, I will say, oh, this is satisfiable, okay. So checking satisfiability of DNF is linear time. It is very easy, and what I have said is, if at least one of the clauses is satisfiable, and a clause to be satisfiable, it does not contain both P and not P for any propositional constant P. That is what we have discussed, right? But the validity problem is difficult here. Why? Because this formula to be valid, what is you have to check? For all possible input, now formula has to be true. Now let us say I have taken 0, 0, 0. Say the first input, if you have say 3 variables, then I have to check whether the formula is true or not, right? For this value, at least one of the terms should be true, right? Now I have to check also for the next one, because I have to ensure that for every input one of the clause is true, right? So that checking cannot be done by just checking one of the clause, because you have to check each of the clause, right? So that means for one input you have to scan the entire formula, but you have 2 to the power n possible input. So effectively you have to check 2 to the power n possible scan to the formula, which is effectively exponential time, right? And that is why the formula is checking validity of a DNF formula is NP complete. Understood? So, I will move on. The next one is CNF, which is just the opposite of DNF. In DNF you have clause which has and those clauses are connected by or. Here it is called conjunction of disjunction of the literal. Okay. Again this is a subset of NNF. So, you have NNF, some of the formula is in DNF, some of the formula is in CNF, and you can have CNF and you can have something other also in NF, right. So, here it is disjunction of the literal. So, this is this. So, you can think about A or not B or C. This is disjunction of literal. This is clause 1 and they are connected by and, right. So, then you have not A or C and not B or not C and so on. So, this is clause 1, this is clause 2, this is clause 3 and you can have multiple clause. So, each of the clause is disjunction of the literals and they are connected by conjunction. This is just opposite of DNF. In DNF what we have? We used to have and here, or is the connection between clauses. Okay. So, this understanding CNF is okay. So, to give an example again, so this is in CNF because you have disjunction of literals, disjunction of literal, disjunctions of literals and they are connected by conjunction, right. To convert any formula into CNF, naturally we will first convert into NNF. We remove all other operators, we bring negation to the atoms and then I will use the distributed property. But here what will distribute? If your formula has disjunction here, conjunction here, because this is not in CNF, this is in DNF, right. So, what I will do, this is equivalent to this, right. So, it will this or will distribute over and. So, it is A or B and A or C, right, they are connected by this. This is in CNF, this is actually in DNF, right. So, in case of DNF, the distributed property was converting a CNF formula over to DNF, and here converting a DNF formula into CNF by distributing or over and here, and in that case it is and over or, right, just the opposite one. So, I can quickly take an example and check this. So, again you have say 2 clause which has again 2 literal for simplicity. So, this is clearly in DNF, right, because you have conjunction of literals and they are connected by disjunction. So, what I will do? I will first distribute x1 over x2 and y2. So, this is x1 or x2 and then x1 or y2 and they are connected by disjunction, and then I will distribute y over x2 and y1 over x2 and y2. So, y1 or x2, y1 or y2 and they are connected by conjunction, right. So, this is in CNF. But you can check again, it is basically you have 2 clauses and I am assuming with 2 literals, it results in 4 clauses in the CNF. If you take again the formula, generic formula of DNF, which has say n clauses, each of them has 2 literals, then the resultant formula would have 2 to the power n clauses, the same way that I have shown for DNF, right. So, again the problem comes, the conversion is good, but I can get a formula which is too big to handle. Okay. So, now I will check the complexity of the satisfiability problem when the formula is in CNF. It is just opposite of DNF. Okay. So, if the formula is in CNF, the satisfiability checking is NP complete. Remember, satisfiability checking in DNF is simple, it was linear time. Why is this? You think about a formula, let us say A or not B or not C, right, and A or C and say B or not C or D and so on, right. So, this is the formula. To check the satisfiability, I have to check is there any input for which this formula is true, right. Now, to have this formula true, each of them has to be true because and is in between. For and everything has to be 1, then only the output will be 1, right. Now I have to take an input, I have to check whether this is true and this is true and this is true, right. If it is not, I have to check the next input and do the same thing. So for an input I have to scan the entire formula once, and now in worst case I have to check the same thing for each possible input. Hence you need exponential time, because your possible input is 2 to the power n if number of literals in your formula is n, right. So that is why this is the complexity will be 2 to the power n, identifying an input for which the formula is true. So that is why this formula checking satisfiability for a CNF formula is NP complete. But the checking validity of the CNF formula is easy, because you again take this formula to check whether this is valid, right. You have to check. So if the formula has to be valid, each of the clause has to be valid, right, because and is in between, right, you have and between. So for all possible input, this particular clause has to be true all the time, right. Now I can check easily whether the formula this, so I can just check the same thing for one clause. And how if a clause can be valid for all possible input? It is only possible if it is has a or not a in it, right. For some proportional constant a, both a and not a present here, and you have disjunction here, right. If a and not a both are present there, no matter what is the other input, it will be always true, right, because either a will be true, then this is true, and if a is false, then this is true, right. So for validity, I have to ensure that each of the clause is valid. Valid means for all possible input this is true, and one clause which is disjunction of literal is valid for all possible input. It is only possible if you have a and not a both here. This is not valid because you have a or not b and c, right. So what I can do, I can just say as n equal to 0, b equal to 1 and c equal to 0. So this will be 0, right. But if you have a term, let us say a or b and not a, right, a or b or not a, this is valid, because if you put a equal to 1, so this will make the clause true, and if you put a equal to 0, this will make the clause true. I do not need to check what is b and all, right. So therefore checking validity is easy, right. So it is linear time. So what you have to do, you have to just check each clause is valid, and a clause is valid if it contains both p and not p for any propositional constant p. Just to check this one, this is valid because you have x1 and not x1 in this clause. So this will be always valid clause, and this is also valid clause, right. So but this is not valid because it has x1 and y1, so this will be false for 0 0, right, and this is also not have this, right. So for 1 and 0 this will be false. So I can prove that this is not a valid formula. So what I have learned from this validity problem of CNF is easy, but satisfiability problem of CNF is NP complete. Okay. So and also we have seen that to convert any arbitrary formula into CNF, the formula size may be exponential, and that is another problem. So to resolve this, we have the Seitin transformation, which effectively can guarantee that no matter what is your initial formula, if you convert into CNF using the Seitin transformation, the size of the formula will be linear increase from the original size, right. So if your original size was say n, it may be 4n, 5n, maybe 2n, but it is not 2 to the power n, right. It will increase the formula size, but it will remain in linear size. So in that case, we will use Seitin transformation, but this Seitin transformation does not occur for DNF. Okay. So we will learn about the Seitin transformation in the next class. When we talk about this Seitin transformation, this definition of equisatisfiable is important, right. What are you doing here? You have a formula f, you are converting into f dash, right. This is what you are doing effectively. Now what you have to make sure that this f and f dash is equisatisfiable. What does it mean? Both formulas are satisfiable or both formulas are unsatisfiable, right. let us understand what is both formulas are satisfiable. It means that, so if say f satisfiable means what? There exists some input for which I satisfies f, right? The formula becomes true under this interpretation. And how I can say this f dash is satisfiable? There exists some input, it may be something else, I dash, right, such that I dash satisfies f dash, right. So, this both are satisfiable means there are some input for which f is true, there is some input for which f dash is true, but it need not to be on the same input, right, it is for some input. So, this is called satisfiable, and similarly if f is unsatisfiable, that means that does not exist any input under which the formula is true, same goes for f dash as well, right. So, our objective is when we convert a formula f to f dash, we have to make sure that the formula f dash is equisatisfiable, because I am checking the satisfiability of the original formula. So, if I ensure that both are equisatisfiable, then if I check the satisfiability of f dash, I will say that f is also satisfiable, right, because if we show f dash is satisfiable and we know these are equisatisfiable, that means there exists some input for which f is also satisfiable, right. So, we will basically try to make sure that the generated formula is equisatisfiable when you convert into a simplified or unified or normal form. Okay. So, we will discuss about this Seitin transforms in the subsequent class, but today before conclusion you might get confused now, right. So, what you have learned that CNF formula validity problem is easy, linear time solvable, satisfiability problem is NP complete, right. On the DNF, the validity problem is NP complete and satisfiability problem is easy, NP linear time solvable, right. Now, you might think that what is the problem? If I have to solve satisfiability, I will convert into DNF. If I have to prove the validity, I will convert into CNF, because both case it is linear time solvable, right. That means, have you solved this decision problem of this proportional constant in linear time, because it is known for NP complete, right. But this is not the case, because I have already discussed that if you take an arbitrary formula, convert into CNF or DNF, it may be of exponential size. So, even if you convert into DNF for satisfiability, but the formula may be exponential. So, this linear time will not help even the formula is exponential. Similarly, if you convert formula into CNF for validity problem, even if your algorithm is smart or polynomial time or linear time easy to solve the problem, but size is formula may be exponential. So, that actually stops. Although we have discussed that Seitin transformation can convert a formula of CNF, arbitrary formula, into CNF of linear increment of size, but satisfiability problem remain NP complete there. So, that will not help, right, and we do not have such conversion for DNF. So, we have not solved this problem, right. So, the problem remain NP complete. So, in the next class we will discuss on Seitin transformation. Thank you.